Welcome everyone. For those of you that don't know me, my name is Greg Croft. I work in circuit design. Today I'm going to talk to you about an introduction to circuit reliability. You can see the talk outline here. There's a lot of stuff I want to try to cover today. Some of this I know pretty well. Some of this I'm not an expert on. So I ask some forgiveness from the other experts in the room if I say something wrong or get something a little off. This is a very broad subject, and there is lots to talk about. And my goal is to discuss as many of the different reliability issues as I can cram into the time that we have available. However, that means I'm going to be jumping around a lot from topic to topic, and I'll probably be only able to hit the highlights. Therefore, I apologize in advance if it seems like I'm rambling aimlessly, and I mean more than I normally do. I know Doug was going there. Where's Doug? Yeah, there he is. Now, if you take a look at an IC, you might think to yourself, what can possibly go wrong? There's no moving parts. And in many ways, you're right. ICs are significantly more reliable than discrete transistors and vastly more reliable than vacuum tubes or relay circuits. However, unfortunately, sometimes things still go wrong. IC reliability issues tend to fall into two major camps. You have the die itself, and then the package that protects the die and provides connections to the outside world. I'm more familiar with the die-related issues, and I'll probably spend more time talking about those. However, I'll attempt to cover one or two of the more common package-related issues also. At the end of this presentation, I've included a glossary of terms you can look through later, although you might want to wait for some night when you're having trouble dozing off. So let's start by talking about ESD. ESD stands for electrostatic discharge. And if you've ever walked across a carpeted floor on a cold, dry day and reached for a grounded doorknob, you've probably experienced an ESD event. The voltages generated during such an event can be fairly high. In fact, you probably won't even feel anything until you get up to 3,000 or 4,000 volts. However, many ICs can be damaged by voltages well below this level. The most common electrical model for an ESD event is called the human body model, or HBM for short. This model was originally developed in the 1800s to help explain the ignition of flammable gas in a coal mine. And it's made up of a charged capacitor and a series resistor. In the 1980s, the DoD issued a standard which set the capacitor value at 100 picofarads and the resistor at 1.5 kiloohms. And that standard is now widely accepted throughout the industry. This model simulates an ESD event by charging capacitor C1 and then discharging it across two pins of the device under test, or DUT, through series resistor R1. And the typical charging voltage would be around 2,000 volts. Now, for characterizing devices, this procedure is repeated many times over and over again to cover all the different pin combinations required by the JEDEC and the NOL standard 883 specs, such as input to output, output to ground, supply to supply. There's just a whole big laundry list of pin combinations that have to be covered. A typical current versus time waveform produced by an HBM ESD event is shown below here, with a rise time of about 5 to 10 nanoseconds, and an RC time constant for the discharge is about 150 nanoseconds. So we're talking maybe 3 RC time constants, 450 nanoseconds for this total pulse. The peak current is basically set by the voltage, the charging voltage, divided by that 1.5K series resistor. So for a typical 2,000 volt pulse, you have about a 1.3 amp peak current. Now, other ESD models exist out there, like the charge device model. We use that all the time. I'm just going to skip over those today due to time limitations, but if you want to talk about them later, I'll be happy to do that. So how can you protect an IC from a 2,000 volt or even higher ESD pulse? And to kind of show that, I want to introduce the concept of ideal ESD protection. And to show that, I want to look at S2 below here. So if S2 is closed, and we're talking a 0 ohm short during an ESD event, all the energy stored in capacitor C1 will be dissipated harmlessly in the external 1.5K series resistor. Since the DUT pins are shorted out, there's no power dissipation in the DUT, and there's no possibility of damage. However, when it comes time for the DUT to function normally, you want switch S2 to open up and look like an infinite resistance with no parasitic capacitance, no leakage current, to allow the DUT to function properly. Now, of course, designing a circuit that acts like a 0 ohm short during an ESD event, and then an infinite resistance with no parasitic capacitance or leakage current after the ESD event, that's kind of bordering on the impossible. However, this concept of an ideal ESD protection circuit can be useful when considering actual protection networks. So the network I'm showing here is called dual rail ESD protection. So in this network, every pin on an IC is connected to a positive rail or a negative rail by current steering diodes. These are sometimes called up-down diodes. And the supply rails are clamped by a shared ESD clamp that goes across the rails. For a positive ESD pulse applied from pin 1 to pin 2, the discharge path for the ESD current would be up through diode D1, across on the positive rail, down through the ESD supply clamp, across on the negative rail, and then up through diode D4. I think you can see that no matter what pin combination you picked here, you're going to see a similar discharge path. Pin 2 to pin 3, pin 1 to pin X. You always go up through a diode, down through a clamp, and up through another diode. These up-down diodes, they're there to steer the current to the ESD supply clamp, and this is a shared ESD supply clamp. And the job of the supply clamp is to act like that ideal switch we saw earlier. During an ESD event, you want the supply clamp to turn on and clamp the on-chip voltage to a low value. However, once the ESD event goes away, you want the supply clamp to turn off and look like an open. And I'll talk more about that later. Let's look at the advantages and disadvantages of this protection scheme. Each pin has a diode to the positive rail and the negative rail. During normal operation, both diodes are reverse biased, and each is going to have leakage current. However, the leakage current from this up diode, it leaks onto the pin, and the leakage current from the down diode, it leaks off the pin. So, it's not an exact cancellation, but to some degree, these two leakage currents somewhat cancel each other out, making the net leakage current contributed by the ESD protection seen from the outside world a little bit lower. So that's a good thing. We're looking at that ideal ESD protection. We'd like it to draw very little leakage current. Pin capacitance is another issue. Let's look at pin 1. Now we've added some capacitance to pin 1 with these ESD diodes. And these capacitors are going to add because they're terminated to AC, they're both terminated to AC ground. So the total capacitance we're adding is C1 plus C2. But these capacitors aren't very large capacitors for two reasons. One is, under normal operation, the diodes are reverse biased. And reverse biased diodes have lower capacitance than forward biased diodes. And another reason is, these diodes are only ever used in the forward direction during an ESD pulse. If you're being used in the forward direction, you don't need as big of an area to handle that pulse. So these diodes can be made relatively small in area. So again, it doesn't add a whole lot of capacitance here to the inputs. By contrast, you look at this big ESD clamp over here. This clamp could be fairly large, and it might have a lot of capacitance. But in this case, you don't care as much. The capacitance is going across the power supply pins. In fact, it may add a little power supply decoupling capacitance, which is generally desirable. So now let's talk about the disadvantages of this architecture. Well, one is you got to run two bus lines all the way around the chip to hook up all these diodes, a positive rail and a negative rail. So that takes up a lot of area. Another potential disadvantage is, let's say you haven't powered the part up yet and you bring power in on an input pin. Now you might be powering up the chip through one of these diodes. And that is not always a problem, but it can be a disadvantage for this type of protection network. I want to show a different protection network that we also use. This is called single rail ESD protection. Instead of a shared supply clamp, what we do is we put a local supply clamp on every pin with a diode to, say, ground. So once again, ESD discharge paths are provided for all pin combinations. For example, if you zap from pin 1 to pin 2, the discharge path would be down through the local clamp, across on ground, and then up through diode D2. You can kind of see, once again, no matter what pin combination you pick here, you're going to have a path, an ESD path for that current. Now this architecture simplifies the hookup. Now you only have one rail you have to run all the way around the chip. However, it adds a little more capacitance to the pins because now you have this local clamp. It's not just these small diodes anymore. And you don't get any kind of leakage current cancellation. All the leakage current is in one direction. So there are some disadvantages and some advantages to this protection scheme. Both of these schemes are in use. It depends on the product. Now I just want to briefly talk about supply clamping. And there's lots and lots of ways to build supply clamps. I'm just going to show one of them here. This circuit is known as a transiently triggered clamp. And it uses the rapid dVdt of an ESD pulse to transiently turn on this large NMOS device and act as a clamp. So during an ESD pulse, again, this could be on any pins, you'll get a rapid voltage rise between the positive rail and the negative rail. However, you can see this capacitor here, it's going to hold the input of the inverter pretty close to the negative rail because a capacitor won't let you change the voltage across it instantaneously. As these rails power up, eventually this inverter is going to turn on, the input's going to be held pretty close to the negative rail, so the output's going to go high. When the output goes high, it turns on this large NMOS device, and this acts as a clamp across the power supplies, very similar to that ideal switch that we talked about earlier. We have an RC time constant here. We want to pick that RC time constant so it's long enough that it'll keep this inverter in the state that we need to keep the device on for the entire length of the ESD pulse. We said those ESD pulses might be 450 nanoseconds. So you'd pick an RC time constant a little bit longer than that, but you don't want it to be too long. Basically what happens is this NMOS starts out in the off state, it gets triggered into the on state by the ESD pulse, and then eventually gets shut off by the RC time constant. So again, it kind of acts like that ideal switch that we talked about earlier. I'm jumping topics here again. Now I want to talk about ESD protection on digital inputs. The schematic shown here is a common technique used for protecting digital inputs from ESD. And this is known as grounded gate NMOS protection. And it can be used as a standalone protection scheme or maybe as a secondary protection in conjunction with the dual or single rail protection networks I showed earlier. Those would be connected outside the resistor here. So the main goal of this protection scheme is to protect these thin gate oxides of these input devices. And these things can rupture if the voltage gets too high on the gate node. Therefore, we keep these voltages pretty low. So if the input gets hit with a negative polarity zap, I'm showing that on the left here, the negative zap relative to ground, the drain to body diode of N1 here will forward bias and limit the voltage on the input of the inverter. That drain to body diode's there all the time. Normally we don't draw them in. I just drew it in here for make it simple to see. So this diode forward biases and protects the gate oxide. This is what if you have a negative zap. However, what happens if you get a positive zap? Well, you say, boy, this MOS device over here, its gate is tied to its source. It's not turning on. So how are you going to protect against a positive zap? Well, as it turns out, there's a lateral NPN bipolar transistor that's underneath this MOS device, and I'll show this on the next slide. And if we get enough current through this junction and R sub, you can actually forward bias the base emitter of this bipolar, and you turn on the bipolar, and that ends up being your protection scheme for a positive zap. And that phenomenon is known as snapback. And again, I'm going to show a little more detail on this next slide here. Okay, so let's take a look at a cross-section of a MOS device. And here we have one. You can see, in addition to the MOS device, there's a lateral bipolar in here. And I've drawn in that lateral bipolar and the substrate resistance. So during a positive zap, the voltage on the drain will rise, but eventually this drain to P-well junction is going to break down, and you're going to start getting current flowing through this path indicated by the arrows. If you get enough drop across this R sub, you can kind of see the R sub is in parallel to the base emitter diode of the bipolar. And if you get 0.7 volts across R sub, it's going to turn on that bipolar, and now you're going to get a lot of current flowing through the bipolar. And this is the VI characteristic of that snapback device. You basically get no current up to a certain level. Then once the lateral bipolar turns on, it snaps back to a lower voltage and it'll conduct a lot of current. Now, once you trigger that NPN, it's going to clamp the inverter input and protect the gate oxides. However, sometimes these parasitic bipolar transistors and the snapback devices themselves, they can be damaged. So that's the job of R1 here. It's in there to current limit and protect the snapback device so you don't cram too much current through the snapback device and end up destroying it. Now, a typical value for R1 might be 200 ohms, but higher, of course, would be better from an ESD standpoint. If your input can take, 5K, 10K, 100K, that's great if you can stick a big resistor in there, but you might not be able to do that from a specification standpoint. I'm switching gears again. Now I'm going to talk about protection of MOS output devices. Now, to some extent, MOS outputs are self-protecting. In many cases, the MOS output transistors, well, they're fairly large, and they're capable of handling a significant amount of current. Now, in addition, the drain-to-body diodes of the output devices, I've drawn them in red over here, they're connected up just like those protection diodes in the dual rail network I showed before, and that kind of helps with the ESD protection. However, there is one potential weakness here. And that's if you zap from, say, VDD to the output or from the output to ground, you have the potential of snapping back one of the parasitic bipolars that are sitting underneath these MOS devices here. And again, we said parasitic bipolars and snapback, you might destroy them. So on the input, we protected that snapback device by adding a current limiting resistor. But this is an output pin. We really can't add a whole lot of current limiting resistor on an output because it's an output. So instead, what we want to do is we want to take advantage of the large size of the output transistor, and we want to spread that ESD current and that power dissipation over the entire volume of the device. However, during snapback, it's common for current to want to crowd in one spot, and that's because we're talking bipolar transistors here. If a bipolar transistor starts heating up, its beta goes up. So let's say one bipolar transistor starts hogging all the current. Its beta goes up, and it says, hey, give me more current. More current goes there, it heats up more, and it says, hey, give me more current again. So you get this positive feedback where all the current wants to crowd in one spot, and that's going to end up destroying the device unless we do something about it. So the most common technique we use to prevent this unwanted current crowding is called drain ballasting or drain extended devices. And drain ballasting adds a small resistor to every drain stripe of a multi-stripe output transistor. And this slide down here shows how that's done just for one stripe. We'll talk about multiple stripes in the next slide. So normally, everything here would be symmetric. You'd have a drain, a gate, and a source. Everything would be symmetric. But what we want to do is we want to add a little bit of resistance here. So what we do is we take the drain contact and we pull it a little further away from the gate, and then we apply a silicide blocking mask in this area to increase the resistance of this N+ material a little bit, and that adds a small resistor in series with this lateral bipolar here. So let's talk about a multi-stripe transistor, since most of these output transistors are multi-stripe. And I'm just going to talk about the NMOS device in this case, but the PMOS device also would be multi-stripe. So in this case, we're saying, what if it's a 4-stripe output transistor? Underneath each stripe, and you can see from a layout standpoint, the gate nodes are drawn in yellow here. There's a bipolar under each of these gates, an NPN. And I've represented those as 4 bipolar transistors over here. What we want to do is we want to add a little tiny resistor in series with each of these bipolars. And the idea is if one of these bipolars starts, crowding all the current or sucking all the current, this drop across this resistor will allow the output node to rise up, and that will allow these other bipolars to trigger and turn on. And you can kind of see from a layout standpoint how that's done. We've come in here and we've taken the drain contacts and we've spaced them further away from the gate. The source contacts are still pretty close to the gate, but the drain contacts are spaced away. And then you might add a silicide blocking mask in here to make the resistance even a little bit higher. So once again, this is drain ballasting or drain extended devices. Very, very common on output devices. Switching topics again. Latchup. What is latchup? Latchup occurs when a parasitic or unwanted silicon-controlled rectifier, that's an SCR, that's connected across the power supplies gets triggered. And an SCR can conduct significant amounts of current until either the power supply is shut down or the IC is damaged. And an SCR is a 4-layer device, a PNPN device, kind of like I show over here. And the regions are called anode gate, cathode gate, and cathode. And this centered diode or blocking diode here is often called the forward blocking junction. The symbol for an SCR, if you're not familiar with it, kind of looks like a diode with a couple extra lines drawn on it to show the gate terminals. And another common name for an SCR is a thyristor, if you've ever heard that term before. So to understand how an SCR works, it helps to represent it as 2 bipolar transistors. You've got a PNP and an NPN transistor. And these transistors are connected such that each of their collectors is connected to the base of the other transistors. And these connections make it possible for this structure to latch in a conducting state, and that turns out to be latchup. Now, if a voltage is applied across the anode to cathode of the SCR, and something triggers one of the bipolar transistors, a positive feedback loop ensues. For example, if a small amount of current starts to flow out of the collector of the PNP, it acts as base current for the NPN. This would cause more collector current to flow in the NPN, which acts as base current for the PNP, causing more collector current to flow, and round this loop it goes. This positive feedback loop turns on both of these transistors very hard, and they will continue to conduct as long as the power supply provides current. In fact, if the power supply is not current limited, the SCR will often conduct so well that the metal lines on the IC will blow, or the SCR will be shorted out by metal migration, and then the metal lines will blow. So if an IC latches and it's not destructive, about the only way to unlatch it is to shut the power supply down. Now, in general, these 4-layer PNPN structures, we don't build them on purpose. However, due to the way many devices are constructed, you end up with unwanted parasitic PNP devices all over your circuit. So in a typical bulk CMOS process, we attempt to kill the potential SCRs by shorting out the base emitter diodes. And I show resistors shorting out the base emitter diodes here. We create those using guard rings, weld ties, substrate ties. The layout designers are very talented at making these resistors very low in value. And if you can get these resistors low enough in value, they kill the effective beta product around this loop. And if you can get that below 1, this thing won't latch because it's not regenerative. The product is below 1. So here's a cross-section of a bulk CMOS inverter with the parasitic SCR drawn in. So you can see And I show the schematic off to the right here. So here's the inverter that we want. And you can see here's the PMOS device, here's the NMOS device. But you have all this extra stuff down here that you don't really want. And that shows up as a parasitic SCR right across the power supplies. Now, what kills this SCR is we drive these resistors to be very low with well ties and substrate ties and guard rings and all that stuff. Now, sometimes the fab will help us out by putting this whole thing on top of a P+ substrate. So you need a low-doped epi region to make all these devices, but you can put it on top of a high-doped substrate. And what that does is it puts a high-doped resistor, meaning a low-value resistor, in parallel to this R sub resistor, and the two resistors in parallel help to drive this R sub resistor very low. I think the fab calls this epi wafers, where you have a high-doped bottom wafer or handle wafer with a thin epi on top of it, low-doped epi, where you make all your devices. But again, this is a technique that you can use to help prevent latchup, is by using high-doped substrates. Now, I've also drawn a very similar inverter using a dielectric isolated CMOS process. So now you see we still have the same devices as before, we still get the same inverter as before, but all this stuff goes away. You don't have all these parasitic devices here anymore. There's no parasitic SCR here. No way for this device to latch up unless you do something really stupid. So this is one of the big advantages of dielectric isolation. Okay, I'm switching gears again. Electromigration now. Electromigration refers to the movement of atoms in a conductor caused by a combination of current density and temperature. And under normal conditions, metal lines on an IC, they'll conduct current reliably for many years. However, electromigration is a potential wear-out mechanism. As electrons flow through a conductor, they normally don't interact much with atomic nuclei because there's a lot of empty space between atoms. However, if you flood an area with a high density of electrons, there's bound to be some collisions that may cause atoms to move. I like to think of this as a ping pong ball hitting a bowling ball. A few ping pong balls won't have much an effect. However, if you flood an area with thousands of energetic ping pong balls, all traveling in the same direction at the same time, you might get a bowling ball to start rolling. I figured Stephen would like that. So this picture down below here is a metal line seen from above. If the current flows left to right, electrons are flowing right to left. And the same current is flowing through all parts of this line. However, the current density is much higher in this thin center section here. So atoms in the center section, they're being pushed out faster than new atoms are moving in. And if you use a DC current and you extend this over a very long period of time, you can see that the metal line is going to thin and eventually break in this section. Okay, so I took some artistic license here, but I think you generally get the idea. EM results are going to be much more irregular than what I showed here. But over time, metal lines can thin and eventually break. Jim Black from Motorola studied this phenomenon way back in 1969, and his findings are summarized in what's known as Black's equation. And this gives a mean time to failure of a metal line, and with a bunch of constants and activation energies and everything else put in here. Now, this equation is not really based on a physical model. It's more of an empirical model used to fit the life test data for a particular technology. And the A, N, and Q parameters, they're just fitting parameters. I just wanted to mention this equation. It's a well-known equation. You'll hear people talk about Black's equation fairly often. So what can be done to avoid electromigration failures? And the first solution is obvious. Have the design engineer make sure not to exceed some predetermined current density limit for that particular process. Okay, so I labeled this guy Greg, okay, but with two G's. But I started looking a little more detailed at the cartoon here, and I said, you know, this guy has a lot of hair, so it can't possibly be Greg. So I think I'm going to have to either go with a Doug or even better, a James. Where's James? Okay. Okay, step coverage. So when calculating current density, it's important to consider step coverage. Most modern fabrication processes create the interconnect and via layers using what's known as a dual Damascene process. And that's a name derived from an ancient technique used in the city of Damascus to inlay metal in pottery. However, you know, we have the modern IC Damascene process, and it cuts trenches and vias, then fills them with metal, and then polishes off any metal that's not inlaid in the trenches, leaving a perfectly flat surface for the next layer of dielectric and metal. And that's how you can do 6 layers of metal or 20 layers of metal, because every one is starting out with a perfectly flat surface. Now, older processes, like we have some locally, don't use this Damascene technique. So you might get topology, meaning steps on the wafer, and then the metal has to flow over those steps. And the metal in these locations often thins down, and this leads to the term step coverage. And I've just drawn 2 examples of what step coverage could look like. Here we have metal flowing over a step, and this is perfect. It's maintaining its full 100% thickness. This would be 100% step coverage. Off to the right here, this is probably a more realistic example where the metal flows over the step and it thins down, and it might thin down to 50% of its original thickness or less, All right, very common. So another way to improve the EM lifetime is to use a material that's less prone to electromigration than just pure aluminum. So studies have shown that adding a very small percentage of copper to the aluminum, and we're talking something small like 0.5%, can greatly extend the mean time to failure of the metal lines. So in addition, it's also common to add a small percentage of silicon to the aluminum. And that's not necessarily for electromigration, that's to improve contact voiding. And I'll just mention that very briefly in a second. So what you end up with a lot of times is aluminum, maybe 1% silicon, and maybe 0.5% copper. Very, very common. And you know, this may not be the exact recipe, but it's something pretty common to that. By the way, contact voiding happens when you get metal making contact to silicon, and if the metal doesn't have any silicon already in it, some of the silicon in the contact will diffuse up into the metal and leave some voids. So you add a little bit of silicon to the aluminum to prevent that metal or silicon migration coming up to into the aluminum to avoid contact voiding. So the physical structure of aluminum can also have an effect on the rate of electromigration. And if you look at an aluminum film under a microscope, it's going to have this grainy appearance shown on the side over here. And these cracks are known as grain boundaries. Now, process engineers know how to adjust the size of these grains by fine-tuning various conditions during metal dep or elsewhere in the fab. And studies have shown that electromigration occurs much faster along these grain boundaries. So if you can make the grains very large compared to the average width of a metal line, very few grain boundaries will run parallel to your current flow. This creates the structure shown on the right here, and that's often referred to as a bamboo structure because it looks kind of like a piece of bamboo. You get a long, skinny metal line with a couple of these grain boundaries cutting across it. So if you hear the term bamboo structure, now you know what they're talking about. As opposed to if your grains were very small, you might get grain boundaries running parallel to your current flow, and you might get a path of accelerated electromigration along these grain boundaries. So it's really good to have very large grains if you can make them. Switching gears yet again, antenna diodes. So we've probably all heard of the term antenna diodes before. However, it may not be 100% clear what that term is actually referring to. And I believe a more descriptive name is gate oxide protection diodes. Now, most modern IC fabs, they use some type of dry etching technique like reactive ion etching to clear away the metal lines and the interlayer dielectric instead of chemical or wet etch. And by wet etch, I mean acid. So using reactive ion etching allows the definition of very fine vias and metal patterns with very straight vertical sidewalls. Oh, it's a beautiful thing. And that's called anisotropic etch. And I show an example of what this looks like over here. Reactive ion etching, when you etch, you get these beautiful straight vertical sidewalls. Oh, that's great. But if you use chemical etch, you'll get a lot of undercutting of the resist. It's very difficult to define very fine geometries. So this reactive ion etching stuff is great. However, one of the disadvantages of this technique is that it imparts charge into the wafer. It's kind of a plasma technique. So normally this charge is drained off harmlessly off the back of the wafer. However, sometimes this charge can build up enough voltage during wafer fab to actually damage the thin gate oxides. So gate oxide protection diodes are small reverse bias diodes connected from the gate of the MOS device to the substrate. And you'll want to connect these things up either in metal 1 or in poly. And you do that so the diode is there for the majority of the dry etch processing steps. If you have 6 layers of metal and you don't hook the diode up until you get to metal 6, well, it wasn't there for metal 1 through 5, and you may have already blown the gates out. So you want to hook this thing up as early in the process as you possibly can. That would be metal 1 or possibly poly. Now, if a negative charge starts building up on this node, I think you can kind of see that this diode is going to forward bias and protect that gate from going too far. Now, if a positive charge starts building up on this node, this gate node is going to rise slightly. However, it turns out that just the leakage current from this diode turns out to be enough to protect the gate oxides during the fabrication process. Now, the term antenna diode comes from a gate node with a very long or wide metal line hooked up to it. And I kind of show that here with this long, circuitous line here. So this long or wide metal line, it can act as an antenna, increasing the amount of charge captured by the gate node and potentially damaging the gate oxide. Most fab processes have rules about how much metal you're allowed to hook to a gate node before an antenna diode is required. Now, we prefer to avoid using antenna diodes altogether, especially in the rad-hard business, because they add an extra junction which could cause an SET event. So our layout designers, they're very skilled at avoiding antenna diodes, and they use creative layout techniques to minimize the metal connections here until eventually we can hook the gate node up to some source or drain terminal somewhere, which will then provide protection without having to add an extra junction. So we're all about having as few junctions as possible. Switching gears yet again, PBTI and NBTI. This stands for positive bias temperature instability or negative bias temperature instability. And both of these are wear-out mechanisms that cause MOS thresholds to change over time by trapping charge in the gate oxide and or affecting the interface states between the gate oxide and the underlying material. For example, let's look at a PMOS transistor under an NBTI condition, which is common for that device when it's in the on state. So you can see here's how we're hooking it up. We're putting ground on the gate, putting 5 volts on the source. So this device is in the on state. Now, if you left that device sit there under that bias condition for a long time at high temperature, you might get some positive charge accumulating under the gate. And this positive charge can increase the threshold of the PMOS device. Now, if you remove the bias or you start to switch, some of that trapped charge can actually dissipate and the threshold can sometimes recover. Now, the time it takes to recover can vary. Might be milliseconds, might be seconds, could be hours. That's part of the insidious nature of this PBTI and NBTI stuff. So this recovery process is also very device dependent. Modern state-of-the-art devices with thinner gate oxides and high electric fields, they may partially recover, but devices fabricated using older processes with thick gate oxides, there's no guarantee that they're ever going to recover from the threshold shifts that you experience with NBTI and PBTI. So these threshold shifts occur in both NMOS devices and PMOS devices. However, PMOS devices are definitely more sensitive, and this applies to both on and off transistors. So what can you do about these threshold shifts? And unfortunately, the answer is not much. It's mostly dictated by the process you're using. However, there are a few circuit techniques that may help a little. If, for example, if you have a critical matched devices, like say an input pair, and you're going to be putting the part in power down mode for an extended period of time. Maybe you're on a spacecraft going to Jupiter and it's going to take you 12 years to get there. So make sure to bias the matched devices exactly the same way, even though those devices are not active. This gives them a better chance of matching once they come out of the power down state. PBTI and NBTI issues have also been observed in digital circuits that use clock gating. Now, clock gating is done to save power. However, when you shut the clock off to part of the circuit, many transistors in that area are put in a DC bias condition where they're more susceptible to threshold shifts due to NBTI or PBTI. And if that's a problem, one potential compromise is to continue to run the clock to minimize the potential threshold shifts. You just throttle it back and run it at a much slower rate to save most of the power. Now, for analog circuits with stacked or cast-coated devices, one theory for minimizing the effects of PBTI or NBTI is to tie all the device bodies to supplies instead of the sources of the stacked devices. And you can see here we have a cascode current mirror. The one on the left here has its body tied to a supply as opposed to tied to the source. Now, I think there's still some debate over the effectiveness of this technique. And, in my opinion, unless you drive the voltage across the gate oxide to zero, you're still going to see either some PBTI or some NBTI effects. Switching topics again. Now I'm going to talk about impact ionization, also known as hot electrons. Impact ionization is the process by which energetic electrons or other particles create electron-hole pairs due to collisions. And these energetic electrons are often referred to as hot electrons, meaning energetic electrons. These hot electrons get their energy from being accelerated by the high electric fields typically caused by the drain to source voltage of saturated MOS devices. You can see here's a saturated MOS device. The high electric field is going to be right in this area that I'm highlighting right there. So in an NMOS device, these energetic electrons can collide with the valence electrons of atoms, creating electron-hole pairs in this area. And in an NMOS device, the electrons, they're going to get attracted to the drain, and the holes, they're going to get attracted to the substrate, or in this case, it could be a body. Now, the modeling group often uses body current measurements when they're characterizing devices to characterize how sensitive a device is to impact ionization or hot carrier lifetime. So these high energy collisions can cause electrons to exit at all angles. And some of these electrons can exit upwards into the gate oxide, and where they can be trapped. And this can generate an electric field that once again alters the threshold of the MOS device. And if enough charge gets accumulated in this area, the device can stop functioning. So this effect can be mitigated just by limiting the drain to source voltage you run at. If you run at a lower drain to source voltage, you may not have enough energy to accelerate these hot electrons up high enough and create these conditions. So if this is a problem, run at lower drain to source voltages. Switching topics again. Electrical overstress, or EOS as it's commonly referred to, is damage to an integrated circuit by exposing it to voltages or currents that are just too high to handle. One of the more common EOS events is caused by simply plugging the part in the socket the wrong way. You can apply power where it shouldn't be, and that can sometimes cause problems. Some ICs have their VDD and ground pins symmetrically located, like the one in the upper right corner here. If the user accidentally flips the part 180 degrees and powers it up, voltage can be applied to the ground pin while the VDD pin is grounded. This can cause a lot of current to flow through the substrate diode, which will typically blow out a metal line or a bond wire. So if you get a customer return, the bond wire is blown out, this is one thing to look at. Another example of electrical overstress is just hot switching or hot insertion. And this refers to dumping a part into a socket that's already powered up or connecting it to a pre-charged capacitor or battery. During a hot insertion, you don't really know what pin will make contact first, and that could cause current to flow on unintended paths and maybe create problems. Now, some chips like our battery management integrated circuits are designed to handle hot plug. However, other chips, they may not be quite as forgiving. A word of warning to the test engineers out there: don't probe die with hot probes. Make sure to power your circuit, your test circuit down, and discharge all capacitors before indexing to the next die. You don't want to bring hot probes down. You'll end up blowing out a whole wafer, perhaps. Hot insertion can result in catastrophic failures, or maybe just cause a mismatch in a sensitive parameter like an input offset voltage, which could show up later as a failure. Another typical EOS event is just caused by voltage spikes on power supplies or input-output pins. And these events can often exceed the breakdown voltage of the chip, and they can contain a lot of energy. And this is going to typically result in some high currents, and these high currents can blow out metal lines. And I show a picture here of a blown out metal line right here. So just an FYI, this is a fairly good way to distinguish EOS damage from ESD damage. Generally, ESD events, they don't have enough energy to actually blow out a metal line like this. If you see a blown metal line, odds are it's an EOS failure. Switching gears yet again. I'm going to talk about high temperature operating life now, and that stands for HTOL. And this is a reliability test applied to ICs to determine their intrinsic reliability. And it stresses the IC at elevated temperatures and their max operating voltages for extended periods of time, maybe 1,000 hours, 2,000, 3,000. And this stress can either be applied dynamically, switching, or statically, DC. And this type of accelerated testing is often used to qualify the reliability of a new device prior to volume manufacturing. Now, there's a shorter duration version of HTOL known as burn-in. And we use burn-in to screen out something called infant mortalities. And I think a typical burn-in time is only 168 hours, or is it different than that now? Okay. I show a typical burn-in oven off to the right here. So the failure rate of an integrated circuit versus time looks like a bathtub curve. And I show a bathtub curve down here. And basically on the y-axis, it's failure rate, and on the x-axis is time. So early on, the failure rate is pretty high. And this population is known as infant mortalities. And this can include manufacturing defects, such as maybe mobile ion contamination. You might have some test escapes in there. You might have some walking wounded parts. Those are parts that have been partially damaged, but they're still functional. So the burn-in is going to accelerate the aging of these parts. So eventually you can screen them out before they get shipped to a customer. So once those infant mortalities have been removed, the resulting population will statistically have a much lower failure rate until the end of life is reached. So I just wanted to very quickly mention qualification testing here. When a new part is developed, typically units from at least 3 fab lots are put through an array of qual tests before being released to volume production. And I just show some of these tests down below here. And I really am not going to talk much about this slide. Just wanted to give you guys an idea of the amount of work that goes into qualifying a new part. This is not an insignificant task. There is lots and lots of testing and lots of work that goes into qualifying a new part. Now, I've already mentioned HTOL testing, and I don't have enough time to talk about all this testing, but I do want to mention HAST testing. So hermetic means watertight or impervious to moisture, and you think plastic is impervious to moisture. However, it really isn't. Ceramic and metal packages, they're generally hermetic, but one test for the susceptibility of plastic to moisture intrusion is called HAST, and that stands for Highly Accelerated Temperature Humidity Stress Test. HAST is sometimes called the pressure cooker test, and it's got high temperatures, high pressures, and high relative humidities. And this test can either be done in biased mode or unbiased mode. And typically it's done for periods of 96 hours, which are roughly 4 days. Now, HAST testing is typically used to qualify a die/plastic package combination before it gets released to general production. I show a typical HAST setup on the right over here. Packaging issues. Packaging comes with its own set of problems, such as solderability, die attach voiding, moisture intrusion, corrosion, delamination, wire sweep, mechanical stress, bond pull failures, just to name a few. I don't have enough time to talk about all these, I'm sorry. I'm just going to hit on some of the more well-known ones. So one of the more well-known problems is if you use gold wire with aluminum bond pads. And if that part went through an elevated temperature, maybe something over 300 degrees C, maybe that's like a high temp solder reflow somewhere, several gold aluminum intermetallics can form. And one of those could be called, is AuAl2. And this is often referred to as the purple plague due to its purple color. And this intermetallic is fairly brittle and it can severely degrade the bond strength, causing lifting. And it's a very bad day if you have the purple plague. So one way to avoid this issue is just use aluminum bond wires with aluminum bond pads. And I think that's what we do on all our hermetic parts. Now, I believe we still use gold ball bonding on our plastic packages, but I don't think we go up to the high temperatures. Last topic today, and I'm kind of running out of time here, is wafer saw. Wafer saw is a critical step in the assembly process where wafers are cut up into individual die. And let's zoom in on the intersection of 4 die and see what that looks like. The scribe line will often contain what's called wafer acceptance test structures, or WAT structures. And these are used in line during the fab to test the wafer for passing and failing it based on a bunch of control limits. Now, these WAT structures, they contain metal lines and probe pads. You know, you don't want any of that metal residue to fall onto your die, shorting anything out. So it's important that these WAT structures be completely obliterated during the saw process. So the saw is going to cut down the center of the scribe line, and the width of the material the saw removes is known as the kerf. We want the kerf to be wide enough so that it completely consumes any metal in the scribe line, but we'd like the kerf to be far enough away from the die to minimize cracking or chipping. Now, we place a crack stop around the periphery of every die, in addition, as a safeguard to prevent cracks from propagating into the die. And a crack stop is basically a very narrow 5-micron opening in the passivation ring that goes around the outside of the die, and it provides a place for cracks to terminate on without propagating further into the die. It's kind of like if you have a crack in the windshield of your car, you can drill a hole right at the end of that crack, and that will stop the crack from propagating further through the glass of your windshield. Okay, conclusion. So today I talked a lot about what can go wrong with ICs. However, the real story is how often things go right. In 1958, the world of electronics was changed forever when Jack Kilby from Texas Instruments invented the integrated circuit. Now, having the ability to co-locate millions or even billions of transistors on the same substrate has increased circuit reliability 1,000-fold. However, along with those advancements came many unexpected challenges. I hope my talk today has given you some insight into a few of those challenges. Thank you very much for your time.